for class assignment number 2, we're reviewing strength of materials. I'd like you to determine the normal stress in the rod BC, also the normal stress in beam AB, and figure out the worst case location. Determine the shear stress in beam AB for the worst case location, the shear stress in pin A, and the shear stress in pin B. Beam AB is 3 inches tall by ½ inch thick. Rod BC is a ½ inch diameter, and pins A and B are both ½ inch diameter. Let's take this one step at a time. Part 1, determine the reactions on beam AB. That's always a good first step. Let's find the reactions, all the external forces. Here's a free body diagram. And probably the first thing to do would be to break force B down into its components. The horizontal components would be 4/5 of B, and the vertical component 3/5 of B. Now let's some moments about A, and that will help us discover B, force B. Well, you notice that the vertical component of B, the 3/5 of B, is acting at 6 feet, creating a positive moment, and the applied load of 1,500 pounds acts at 4 feet, creating a negative moment. Also notice that I'm including the units in the equation. That's probably a habit that you haven't gotten into yet, which is a good habit to get into. Include the units when you're making computations. Some of you are also in the habit of using your TI-89 to do all your algebra and solving. And probably if I were to give you any kind of significant algebra problem, you would either be really slow at it or you wouldn't remember how to do it at all. When you go to take the FE exam, you won't be able to use your TI-89. So let me walk you through some strategic ways to do algebra and make it quick, so that when you take the FE exam during your senior year, you'll be fast and won't have to worry so much about the time constraint. Well, if I'm going to do algebra on this equation, the first thing that I will do is collapse anything into one single number that I can. For instance, notice I took the 3/5 and the 6, collapsed it into 1 decimal 3.6. Also notice that I took the 1,500 pounds and multiplied it by 4 to collapse it into a single number. And also notice that I'm still carrying my units. Now the algebra is much easier. I'll simply take 6,000 divided by 3.6, and again carrying the units, I notice that feet cancel, and I'm left with 1,667 pounds. That's force B. Now let's go ahead and sum forces in the x direction, so that I can find AX. Well, we might as well put those components as numbers as well. 4/5 of B is 1,334. 3/5 of B is 1,000 pounds. Now let's sum forces. Forces in the x direction. Well, I have AX in the negative x direction, and I have 1,334 in the positive, which tells me that AX is 1,334 pounds. Let's sum forces in the y direction. Well, I have AY in the positive, the 1,500 pound load in the negative, and the 1,000 pound reaction at B, the vertical component, in the positive direction. Do a little algebra, and we find that AY is 500 pounds. Go ahead and give yourself 1 point if you got those reactions correct. Part 2, determine normal stress in rod BC. Go ahead and pause the video and work that out. Okay. Well, the normal stress is the force in the rod divided by its area. It's just an axial load. The force is 1,667 pounds. The area, notice for area, I'm using pi d squared over 4. That's the way engineers do it. A mathematician would use pi r squared. But an engineer knows that you can't measure a radius. You'll have to measure the diameter anyway. So let's have an equation for area that uses diameter. That results in 8,490 psi, or pounds per square inch of stress in rod AB. Give yourself a point if you got that right. Part 3, draw the shear and moment diagrams of beam AB and determine the maximum values. Go ahead and pause the video and work that out. Okay? Well, let's do shear diagram first. If you remember, a point load causes the shear to jump up or down in the direction of the point load. So in this case, we jump up to 500 pounds. The shear stress doesn't change in the beam until you get to the applied load of 1,500 pounds, at which point it jumps down by 1,500 to negative 1,000 pounds. So the shear load in the beam at that point is negative 1,000 pounds. Continues until you get to point B, where it jumps back up to 0. There's the shear diagram. The moment diagram, we start at point A, which is a pin connection and can't support moment, so we know at point A the moment is 0, and that it slopes upward linearly. And if we take the area under the shear curve, we can find the value of the moment at that point. So we know that the moment at the location where the load is applied is 2,000 pound-feet. And we also note that at point B it is a pin connection, so that it slopes back down to 0. Go ahead and give yourself 1 point if you got the shear and moment diagram correct. Part 4. Determine the maximum bending stress in the beam and show the location on the beam where this occurs. Go ahead and pause the video and work that out. Okay. The maximum bending stress occurs at the outermost fiber of the beam. If we remember, at the neutral axis there is no bending stress. Either the top or the bottom of the beam will have maximum normal stress. And at the top of the beam it will be compression in this case, and the bottom of the beam tension. The reason I chose the point at the place where the load was applied is we notice that that's where the moment is the largest. So not only have we chose the outermost fiber where bending stress is the largest, but we've also chose the location where the load was applied, which is where the moment is the maximum. And bending stress is given by the equation mc over I, where m is the moment, 2,000 pound-feet. C is the distance from the neutral axis to that outer fiber. And if the beam is 3 inches tall, then the distance from the neutral axis to the bottom of the beam is 1.5 inches. I is the moment of inertia, which is simply a measurement of how much material and how far away it is from the neutral axis. In other words, it's a measure of how strong the beam is. For a rectangle, if you remember, moment of inertia is base times the height cubed divided by 12. BH cubed over 12. Now, good thing we're in the habit of carrying our units with our equation, because we can see that this equation will not work out to psi of stress because we have feet there in the numerator. We've got to convert feet into inches, and then we can see that our units will work out to be pounds per square inch, resulting in 32,000 pounds per square inch of stress. Go ahead and give yourself a point if you got that right. Part 5, determine the maximum axial stress in the beam. Go ahead and pause the video and work that out. Okay, the maximum axial stress is simply force divided by the area, the axial force divided by the area. In this case, the axial force in the beam is the 1,334 pounds, and the area of the beam is a 1/2 by 3 inch rectangle, resulting in 889 pounds per square inch of stress. Give yourself a point if you got that right. Okay, part 6, determine the maximum shear stress in the beam and show the location where this occurs. Go ahead and pause the video and work that out. Okay, Shear stress in a beam, we call it transverse shear, and that occurs at the neutral axis. Normal stress, bending stress, is worst at the outer fibers. Shear stress is worst at the neutral axis. And also notice that my element that I've chosen is just slightly to the right of where the load is applied. If I were just slightly to the left of where the load is applied, the shear force would only be 500. Just to the right, the shear force is larger, 1,000. The shear stress is given by the equation VQ over IT, where V is the shear force. In this case, we're looking for the worst shear force, which is 1,000 pounds. That's why we've chosen the location we have. Q, the worst Q, of course, is at the neutral axis. And a definition for Q is the moment of area above or below the neutral axis. So if I were to take the area below the neutral axis, that's 1/2 inch by 1.5 inches. And then take the moment of that area, means take the area times the distance to its centroid. In other words, 1/2 inch by 1.5 inches is the area, times the 3/4 of an inch would be the moment of that area. I, again, is the moment of inertia, the h³ over 12, and T is the thickness, 1/2 inch. That results in 1,000 pounds per square inch of stress. Give yourself a point if you got that right. Part 7. Draw the state of stress on the two elements shown. Go ahead and pause the video and work that out. Okay. Let's start with the element on the bottom of the beam, where we determined bending stress. And we also should recognize that the normal stress on that fiber is the bending stress plus the additional axial stress. That bottom element is in tension due to bending and tension due to axial stress. So we'll add the 32,000 to the 889 and find that the total normal stress on that element is 32,889. The element at the neutral axis has some shear stress, the transverse shear stress, 1,000 psi, and don't forget that it also has axial stress on those faces of 889 psi. Go ahead and give yourself 1 point if you got that right. Also, in order to get that point, make sure on the shear stress element that your arrows are drawn in the correct direction. The arrow on the right face of the element is upward. Part 8. Determine the shear stress in pin A. Go ahead and pause the video and work that out. Okay, well, the first thing to do is to figure out the total load on that pin, which is the vector sum of AX and AY, the square root of the sum of the squares, 1,425 pounds on pin A. We also know that the way it's connected to the beam is that that pin is in double shear. So the force in that beam is divided by 2 pin areas. So we take the 1,425 pounds and we're going to divide it by 2 cross-sectional areas of the pin, resulting in 3,629 psi of stress. Give yourself 1 point if you got that right. Part 9. Determine the shear stress in pin B. Well, we notice that pin B is only in single shear, so the force divided by the area will give us that shear stress. Force of 1,667 pounds divided by the area of the pin results in 8,489 psi of stress. Give yourself 1 point if you got that right. And part 10, go ahead and come to class and participate in the discussion, and that's worth 1 point. So BC-2 is worth a total of 10 points. We'll see you in class.